galaxy is old, older than our species, older than our planet, older than almost everything we can imagine. The Milky Way formed over 13 billion years ago. Earth is only 4.5 billion years old. Human civilization, a few thousand years. If life is not impossible, if intelligence is not a miracle that happens only once, then statistically, we should not be first. There has been time, more than enough time. Time for civilizations to rise, time for them to master energy, time for them to spread across stars, and yet, the sky is silent. No probes, no signals, no megastructures blocking distant starlight, no visible engineering scars on the galaxy, just background radiation, just cold physics. Some have asked a dangerous question. What if we are not early? What if others came before us and failed? What if entire civilizations rose, mastered their worlds, reached outward, and then vanished? There is no evidence that a lost civilization fled here. No proof that we are the descendants of cosmic refugees, but the silence itself forces a harder question. If civilizations can arise, why don't they persist? If intelligence can build technology, why doesn't it endure? This episode is not about aliens. It is about something far closer. It is about the lifespan of complexity. Because whether we are first or one of many, one fact remains. Every civilization that has ever existed has either ended or is still on its way there. The real question is not whether civilizations rise. The real question is, why do they fall? Before we can ask why civilizations end, we need to define what a civilization is, not culturally, not morally, not philosophically, structurally. A civilization is an energy system. It captures energy from its environment, converts it into work, and uses that work to build structure, cities, infrastructure, agriculture, data networks, industry, satellites orbiting a planet. None of these are ideas. They are energy flows organized into stability. At its core, a civilization does three things. It extracts energy, it increases complexity, it coordinates large numbers of individuals. Remove any one of these, and the system collapses. Energy is obvious. Without surplus energy, there is no specialization. Without specialization, there is no technology. Without technology, there is no scaling. But complexity is the hidden variable. As civilizations grow, they do not just get bigger, they get more interdependent. Supply chains stretch across continents. Food depends on logistics. Logistics depends on fuel. Fuel depends on global trade. Trade depends on financial stability. Finance depends on trust. Each layer increases efficiency. Each layer also increases fragility. A small village can survive isolation. A hyper-connected global system cannot. This is the paradox of progress. The more powerful a civilization becomes, the more moving parts it must keep stable. And stability is not free. It requires coordination. Coordination requires communication. Communication requires shared trust structures. Shared trust structures require institutional integrity. Break coordination and energy still exists, but it cannot be directed. Break energy flow and coordination becomes irrelevant. Civilization is not culture. It is managed complexity sustained by continuous energy input. And complexity does not scale indefinitely without cost. Every additional layer adds efficiency and risk. This leads to a dangerous assumption most societies make. If we are more advanced, we must be more secure. History does not support that belief. In fact, the opposite pattern often appears. Growth amplifies capability, but it also amplifies consequence. The question is not whether complexity increases power. It does. The question is whether complexity increases resilience at the same rate. Because if power rises faster than stability, a civilization does not fail slowly. It fails systemically. And once failure becomes systemic, recovery is no longer guaranteed. That is a structure we are dealing with, not destiny, not prophecy, structure. Civilizations rarely end in a single moment. They don't usually explode. They don't vanish overnight. They unravel. From the outside, collapse looks sudden. From the inside, it feels gradual, until it isn't. History gives us patterns, not myths, not moral lessons, patterns. Take the Roman Empire. Rome did not fall because of one invasion. It expanded beyond its logistical limits. Military spending outpaced economic stability. Political fragmentation weakened coordination. Currency was debased to manage short-term pressure. Infrastructure became harder to maintain across vast distances. For centuries, the system adapted, until adaptation itself became too expensive. External pressure, invasions, did not create weakness. They exposed it. Now consider the Maya civilization. Advanced astronomy, urban centers, agricultural engineering. But prolonged droughts increased environmental stress. Population pressure strained food systems. Internal conflict fragmented political cohesion. No single catastrophe ended them. Environmental stress plus internal instability crossed a threshold. The cities were abandoned. The pattern repeats. Complex systems expand. They optimize for efficiency. They become dependent on long supply chains and layered coordination. Then stress arrives, sometimes environmental, sometimes economic, sometimes political. The stress does not need to be enormous. It only needs to hit a system that has little redundancy left. This is the critical principle. Civilizations do not collapse because they are primitive. They collapse because they are complex. The very mechanisms that create power, scale, specialization, integration, reduce local autonomy. A small agrarian society can fragment and survive. A globally interlocked system cannot fragment without severe loss. Collapse, in structural terms, is not destruction. It is a rapid reduction of complexity. Institutions fail. Trade contracts. Knowledge disperses. Population declines. The system shrinks until it reaches a level it can sustain again. The key insight is this: collapse is often not a single blow. It is accumulated fragility meeting stress, external shock plus internal weakness. And here is the uncomfortable connection. The more interconnected a civilization becomes, the more synchronized its risks become. Local failures stop being local. They propagate. History's fallen empires were regional. Their collapses were devastating, but contained. For the first time in history, we operate a civilization that is planetary in scale, which means when stress comes, it does not arrive at the edges, it arrives everywhere at once. Human civilizations collapse within history, but Earth has a longer memory. Long before cities, long before agriculture, long before intelligence began shaping ecosystems, the planet erased dominance multiple times. There have been 5 major mass extinctions. Each one removed a vast percentage of life on Earth. Each one reset ecological complexity. Each one proved the same point. Dominance is temporary. The most famous example came 66 million years ago. An asteroid, roughly 10 kilometers wide, struck near what is now the Yucatan Peninsula. The impact triggered global fires. Atmospheric dust blocked sunlight. Food chains collapsed. The event is known as the Cretaceous to Paleogene extinction. Non-avian dinosaurs had ruled the planet for over 160 million years. They were not weak. They were not poorly adapted. They were successful. And success did not protect them. Evolution does not guarantee permanence. It guarantees only temporary fit. Other extinction events were driven by different forces: massive volcanic eruptions, rapid climate shifts, ocean acidification, atmospheric chemistry changes. None of them were intentional. None of them were targeted. They were systemic disruptions large enough to destabilize the biosphere. Life recovered, but not in the same form. This matters for one reason: civilization sits on top of biology. We are not separate from planetary systems. We depend on climate stability, atmospheric balance, and ecological continuity. An asteroid does not distinguish between reptiles and industrial societies. A supervolcanic eruption does not pause for technological maturity. For most of Earth's history, life survived by adapting. But adaptation works slowly. Planetary-scale shocks can arrive suddenly. The difference between dinosaurs and humans is not immunity, it is awareness. We can detect near-Earth objects. We can model climate systems. We can study solar activity, but detection is not defense, and awareness does not equal preparation. Mass extinctions teach a blunt lesson: long-term survival is not guaranteed by success. It is guaranteed, if at all, by resilience against rare but catastrophic events. A species can dominate for millions of years and still disappear in a geological instant. A civilization that has existed for a few thousand years should not assume it is exempt. The planet has reset complex life before. It can do so again. The real question is not whether external shocks exist. They do. The question is whether a technological civilization can become robust enough to survive one. External shocks are indifferent. Asteroids do not negotiate. Volcanoes do not calculate. Solar flares do not intend harm. But for the first time in Earth's history, a species has become a source of planetary-scale risk. Not by malice, by capability. Nuclear weapons were built in less than a century. Within decades, enough warheads existed to disrupt global climate through nuclear winter scenarios. No asteroid required, no cosmic accident, just escalation. The same pattern appears in biotechnology. The tools required to edit genetic material have become cheaper, faster, and more accessible. Research that once required state-level resources can now be conducted in smaller laboratories. Most work is benign. Much of it is beneficial. But the barrier between innovation and catastrophe has narrowed. Artificial intelligence follows a similar curve. Systems are becoming capable of autonomous decision-making in domains once reserved for human judgment. Financial systems, military coordination, infrastructure management. When capability scales faster than oversight, mistakes amplify. The danger is not necessarily rebellion, it is misalignment. A system optimizing the wrong objective at large scale can destabilize critical networks before correction is possible. Climate change adds another layer. It is not an extinction event by itself, but it increases systemic stress, agricultural instability, water scarcity, migration pressure, political fragmentation. Each factor alone may be manageable. Combined, they strain coordination, and coordination is what keeps complexity alive. The pattern here is different from asteroid impacts. These risks are endogenous. They emerge from the same engine that powers progress. Energy expansion increases output. Output increases capability. Capability increases leverage. Leverage increases consequence. In pre-industrial societies, mistakes were local. Today, errors propagate globally. A financial collapse in one region affects supply chains worldwide. A pathogen emerging in one city crosses continents in days. An algorithmic failure can ripple across markets instantly. The paradox is this: the technologies that increase resilience also increase vulnerability. Nuclear power provides energy. It also introduces catastrophic failure modes. Global trade reduces scarcity. It also synchronizes risk. Advanced computation improves forecasting. It also centralizes decision-making. This is not an argument against technology. It is an observation about scale. When power grows exponentially, but governance evolves incrementally, the margin for error shrinks. External threats test survival. Internal threats test judgment. And for the first time, a civilization holds tools capable of ending itself without any help from the cosmos. There is a pattern hiding beneath everything we've discussed. It is not nuclear weapons. It is not biotechnology. It is not artificial intelligence. It is timing. Technological capability grows exponentially. Human coordination does not. Energy extraction doubles. Processing power scales, automation accelerates, but governance structures evolve slowly. Cultural adaptation lags. Global consensus fractures under pressure. This creates a widening gap. The gap between what we can do and what we can responsibly manage. In early civilizations, this gap was small. A Bronze Age society could not destroy the planet. Its tools limited its reach. Today, reach is no longer the constraint. Judgment is. The most dangerous phase of any civilization may not be its decline. It may be its adolescence, a period when power expands faster than wisdom, when tools outpace restraint, when capability exceeds coordination. This is the power control gap, and it does not require malice to become lethal. It requires miscalculation. Escalation theory shows how quickly rational actors can drift into irreversible conflict. Biological systems show how small mutations can cascade under the right conditions. Complex networks demonstrate how tightly coupled systems can fail abruptly when stress crosses a threshold. In each case, the issue is not intention. It is insufficient control over amplified consequence. The more interconnected a system becomes, the more nonlinear its failures become. Small triggers, large outcomes. A diplomatic misunderstanding in a nuclear age is not equivalent to one in the 14th century. An engineered pathogen is not equivalent to a medieval plague. An autonomous financial algorithm is not equivalent to human traders making isolated decisions. Power has scaled. Control has not scaled at the same rate. And here is the critical shift in perspective. Civilizations do not usually end because they lack intelligence. They end because they overestimate it. They assume that because they solved previous crises, they will solve the next one. But each new layer of complexity raises the stakes. The more powerful a civilization becomes, the less room it has for error. When power is small, mistakes are survivable. When power is planetary, mistakes are existential. This is not prophecy. It is structural asymmetry. If the growth of capability continues to outpace the growth of coordination, the system enters a volatile regime. And volatility, at scale, does not remain theoretical for long. Collapse is not triggered by power alone. It is triggered when complexity becomes brittle. Every civilization increases efficiency over time. Supply chains shorten costs. Energy grids centralize distribution. Data networks synchronize coordination. Food systems optimize yield. Redundancy is reduced because redundancy is expensive. Backup systems are trimmed. Local autonomy is replaced with integration. Slack disappears. Efficiency rises. Resilience quietly falls. This trade-off is rarely visible during growth. During expansion, interdependence feels like strength. Global trade reduces scarcity. Digital networks reduce friction. Just-in-time logistics reduce waste. Everything works until something interrupts it. A drought in one region affects food prices worldwide. A cyber attack halts energy infrastructure across borders. A financial shock ripples through interconnected markets in hours. In tightly coupled systems, failures propagate faster than solutions. This is the fragility threshold, the point at which complexity stops buffering shocks and begins amplifying them. In simple systems, damage is local. In highly integrated systems, damage synchronizes. A medieval city could burn while others continued. A planetary civilization shares grids, trade routes, satellite networks, communication layers. Local disruption becomes systemic stress. And when systemic stress crosses a threshold, the system does not degrade smoothly. It cascades. Infrastructure failure leads to economic instability. Economic instability leads to political fragmentation. Political fragmentation reduces coordination. Reduced coordination worsens infrastructure recovery. Feedback loops emerge. The system feeds on its own instability. This is how collapse accelerates, not as a single catastrophic moment, but as a series of compounding failures that outpace recovery capacity. The critical insight is this: complexity increases problem-solving capacity. But beyond a certain point, complexity also increases failure velocity. There exists a narrow window where a civilization is advanced enough to wield immense power, but not yet robust enough to absorb planetary-scale shocks. That window may be brief. Too little complexity and a civilization cannot scale. Too much poorly managed complexity and it becomes fragile. The fragility threshold is not visible on a calendar. It is visible only in stress tests. And most civilizations do not recognize they have crossed it until stress arrives. If collapse is structural, then survival must also be structural. At planetary scale, there is only one long-term currency: energy. Civilizations do not persist because they are moral. They persist because they manage energy efficiently and at increasing scales. This idea was formalized in what is known as the Kardashev scale. A Type 1 civilization controls the energy resources of its planet. A Type 2 civilization harnesses the energy of its star. A Type 3 civilization operates at the scale of its galaxy. These are not science fiction categories. They are energy budgets. Humanity is not yet Type 1. We still rely on fragmented extraction. We do not fully control planetary climate systems. We do not regulate solar input. We do not deflect large asteroids with certainty. We are powerful, but locally. The logic is straightforward. A civilization confined to one planet is vulnerable to planetary events. A civilization confined to one star is vulnerable to stellar evolution. Stars do not burn forever. Over billions of years, even stable stars change. If survival is measured in cosmic time, remaining in planetary is temporary. But here is the harder question: do civilizations typically survive long enough to climb the energy scale? Or does the fragility threshold arrive first? Because advancing from planetary dependence to interplanetary redundancy requires massive coordination. It requires stable institutions, long-term planning, and restraint during technological adolescence. Reaching higher energy scales increases survival potential. It also increases destructive capacity. A civilization capable of stellar engineering would also be capable of unprecedented self-damage if coordination fails. This is the double edge of energy scaling. More energy means more options. It also means more irreversible mistakes. Which leads to a sobering possibility. Perhaps the silence of the galaxy is not because civilizations never arise. Perhaps it is because few survive their transition phase. The leap from planetary fragility to cosmic resilience may be the most dangerous stage. If a civilization crosses it, it may endure for astronomical timescales. If it fails, it leaves no lasting signal. Energy determines reach. Coordination determines whether that reach becomes expansion or collapse. Cosmic fate is not written in prophecy. It is written in whether a civilization can scale its stability as fast as it scales its power. If collapse is structural, then survival cannot be accidental. It must also be structural. Hope is not a strategy. Good intentions are not insulation. Technological brilliance alone is not protection. Survival at planetary scale requires design. The first condition is redundancy. A civilization confined to a single biosphere is fragile by definition. One planet, one climate system, one chain of ecological dependencies. Redundancy means diversification, multiple energy sources, multiple food systems, multiple communication layers, eventually multiple habitats. Not for prestige, not for symbolism, for risk distribution. The second condition is detection before impact. Asteroids are survivable if detected early. Solar storms are manageable if infrastructure is hardened. Pandemics are containable if surveillance systems are global and rapid. Catastrophe is not always the problem. Unpreparedness is. The third condition is governance proportional to power. As capability scales, oversight must scale with it. Nuclear arsenals require strict command structures. Biotechnology requires global safety norms. Artificial intelligence requires alignment mechanisms that evolve alongside capability. If power grows faster than coordination, the gap reopens. The fourth condition is energy stability. A civilization that cannot maintain stable energy flows cannot sustain complexity. Energy transitions must be deliberate, not chaotic. Grid resilience, storage systems, distributed generation, these are not engineering luxuries. They are survival infrastructure. The fifth condition is long-term thinking. Civilizations often fail because they optimize for the next quarter, the next election, the next crisis. But planetary survival requires planning across decades and centuries. This is rare. It demands institutional continuity stronger than short-term incentives. None of these guarantees immortality. There is no permanent safety, but together they shift probability. Survival is not about eliminating risk. It is about managing it faster than it accumulates. The universe does not reward ambition. It does not punish arrogance. It is indifferent, which means resilience must be intentional. The final question is not whether collapse is possible. It is whether a civilization can recognize its own fragility before stress forces recognition upon it. Because once cascading failure begins, options narrow quickly. Survival is not automatic. It is engineered. The galaxy is silent, maybe because civilizations are rare, maybe because they are short-lived. Maybe because the leap from planetary power to cosmic resilience is harder than it looks. We don't know. But we do know this. Every civilization in history expanded. Everyone increased complexity. Everyone believed it had adapted. And everyone eventually faced limits. Some limits were environmental. Some were political. Some were technological. None were mystical. Collapse is not a curse. It is not divine punishment. It is not destiny written in the stars. It is a structural outcome when fragility meets stress. For the first time in Earth's history, a species understands this pattern while still inside it. We can see the energy scale. We can model extinction risks. We can calculate asteroid trajectories. We can simulate climate systems. We can analyze network fragility. Awareness does not guarantee survival, but it changes the equation. The universe does not decide our fate. Probability does. If power grows faster than coordination, the outcome narrows. If resilience grows alongside capability, the horizon expands. Medeniyetlerin sonu bir kehanet değildir. It is a risk profile, and risk profiles can be altered, not by hope, not by fear, by design. The real question is not whether civilizations fall. The real question is whether one can learn fast enough to avoid becoming another silent statistic in a very old galaxy. Fate is not prophecy, it's probability management.